Greetings, everyone. My name is Dhruv Bhardwaj, and today I am thrilled to present our project Optimizing Navigation, Evaluating Pathfinding Algorithms for Efficient Route Planning. This endeavor is a collaborative project, and I am proud to be part of a team that includes my talented peers Arijit, Akhil, and Goutham. In our interconnected world, the ability to plan routes efficiently holds immense value across various sectors. Our project delves into the comparative study of key pathfinding algorithms, BFS, DFS, Dijkstras, and A star, to identify the most effective strategy for minimizing time travel and costs in navigation scenarios. These algorithms have been taught to us and are part of Module 5 and 6 of our course. The goal of our research is twofold: to deepen our understanding of these complex algorithms and to unlock practical solutions that can be applied in real world contexts, enhancing the efficiency of transportation networks and data flow systems. Now, I shall be taking over for A star algorithm overview. A slight introduction. The A star algorithm is popular and highly effective pathfinding and graph traversal algorithm. It's widely used in various applications such as AI for games, robotics, networking routing, where finding shortest path is essential. Coming up to how the algorithm works, the A-star algorithm it combines the features of Dijkstra's algorithms, which is good at exhaustive searching, and greedy best first search, which is fast but not always accurate, to efficiently compute the shortest path. It uses heuristic function to estimate the cost of the cheapest path from a node to the goal. This function guides the algorithm to explore the fastest paths that are more likely to lead the solution. Nodes are evaluated based on their cost, which is the G score, and estimated cost to reach the goal, which is your H score. And summing these two gives us the F score, G plus H, which determines the node's priority. Now let's move on to algorithms complexity. Uh, Time complexity of A star depends on the heuristic. In the worst case, it is exponential, but with a good heuristic, it can significantly reduce, often to polynomial time. As for space complexity, it is also dependent on heuristics and can be uh, exponential in worst case due to the need to store all the generated nodes in the memory. As for advantages for this algorithm, it is highly efficient and effective for many pathfinding problems. It offers a balance between speed and accuracy, and it is adaptable to various contexts with appropriate heuristic. And as for disadvantages, performance heavily depends on heuristics accuracy, and it can be memory intensive due to storing all the open nodes. Now let's go on to the code explanation. This is an A star implementation that I'll be explaining, and later on in the video, my my group mates will explain the other form of algorithms that we have used, plus the final combination of all our algorithms. So this is a sample graph, and this is where I have defined the heuristic and A star algorithm. In the heuristic function, I have taken Euclidean distance. Now, to test the algorithm, I have used a test graph and I have defined some edge cases. In test case 1 or edge case 1, we find the path between adjacent nodes. As you can see, then if it's A and B, then cost is 0 and node explode is 2. Path where start and end nodes are same, then the cost is 0 and node explode is 1. And if there is no path between the two nodes, then there is no the nodes explode is 0. Now, as for user input, now let's find the shortest path between A and H. So we get the shortest path with the cost, node explode, execution time, and current memory usage.
Alright, let's dive into the best first search algorithm, a powerful tool for searching and traversing tree or graph data structures. The key idea behind BFS is that it explores the graph level by level. It starts from a source node and first examines all its neighboring nodes before moving on to the next level of nodes. This is done by using a queue to keep track of the nodes that need to be explored. The queue is defined as a list of Here's how the algorithm works. We start at the source node and add it to the queue. We then dequeue a node from the queue and examine its neighbors. Any unvisited neighbors are added to the back of the queue. We repeat the steps 2 and 3 until the queue is empty, at which point we have explored all the nodes at the current depth level. Once that's done, we move on to the next level of nodes and repeat the process. This level by level exploration continues until we either reach the goal node or exhaust all the nodes in the graph. The time complexity of the BFS is O of V plus C, where V is the number of vertices and E is the number of edges. This is because we need to visit each vertex and edge once. The space complexity is O of V, as you need to store all the vertices in the queue. Some key advantages of BFS are that it is simple to implement, guarantees the shortest path on unweighted graphs, and it is useful for layer by layer analysis. However, it can be slower on large datasets and requires more memory to the queue. Overall, BFS is a fundamental algorithm which is widely used in various applications, from finding the shortest path in a maze to implementing social media features like news, feed, etc. This level by level exploration makes it a powerful tool in the world of data structures and algorithms.
I'm going to talk about Dijkstra's algorithm. Dijkstra's algorithm is used to find the shortest paths from a starting node to all other nodes in a graph. It works on both directed and undirected graphs, but the edges must have non-negative weights. This is the condition. The essence of Dijkstra's algorithm is to repeatedly pick the vertex with the minimum distance estimate, update the distances of its neighbors, and finalize the distance when a vertex is chosen. The animation over here shows the various steps that are followed in performing the stress algorithm. The steps in a nutshell are as follows. We start with the distance by setting the distance to all the vertices as infinity and the distance to the starting vertex as 0. Then at each step, we select the vertex with the minimum distance that has not been finalized yet, followed by updating the distance to neighboring vertices of the selected vertex. Once a vertex is selected and its distance is updated, its shortest path from the source is finalized. The algorithm has a time complexity depending on the data structure used to implement it. So when using a binary heap or a Fibonacci heap for the priority queue, the time complexity is big O of V plus E, where V is the number of vertices and E is the number of edges in the graph. This complexity arises from the fact that each edge is processed once, and for each edge, the algorithm performs a decrease key operation on the priority queue, which itself has a cost of big O of log V time with a binary heap, or it'll have a big O of 1 time with a Fibonacci heap. If a simple array or list was used as the priority queue, the algorithm scans the entire list to find the minimum distance vertex in each iteration, and the time complexity would have been big O of V squared, as scanning the list for the minimum element takes big O of V time, and this is done V times. The space complexity of Dijkstra's algorithm is big O of V for the priority queue and big O of V for the distance array, resulting in a total space complexity of big O of V. We have implemented a code example of Dijkstra's algorithm in here. If you look at the graph given here, it has a pictorial representation as given here. This image is a simple pseudocode that tries to explain the working of Dijkstra's algorithm. We also have a Python code implementation underneath. We're using a priority queue here and using the same graph shown above as input to this function, and it will generate the distance of A to every other node in the graph. So you can see that from A to A, the distance is 0, A to B, it's 2, and A to F is 5, and so on. The disadvantages of using Dijkstra's algorithm are limited to non-negative edge weights. One of the main limitations is it cannot handle graphs with negative edge weights, as I mentioned at the beginning. We also require knowledge of the entire graph to compute the shortest path from the source node to all other nodes. In some applications, this may not be practical, especially in dynamic or large scale networks. We have high memory requirements since we have a space complexity of big O of V. It still requires storing distance values for all the nodes, which itself can be a drawback in memory constrained environments.
Hi, myself Gautam. I'm going to say about the depth first search. Depth first search is a graph traversal algorithm used to systematically explore nodes and edges in a graph structure. It operates by starting at a chosen node and explores as deeply as possible along each branch before backtracking. DFS is particularly effective for tasks such as maze solving, cycle detection, and topological sorting due to its simplicity and efficiency. The highlighted code snippet defines a function named DFS, which implements the depth-first search algorithm to find a path from a start node to a goal node within a given graph. At the start, we initialize some variables, including the start time, to record the beginning of the search, and a visited set to keep track of visited nodes, and also initialize a stack with a list containing only the starting node. During the main loop, the algorithm operates by popping a path from the stack and checking if it matches the goal node. If a match is found, the function returns the current path along with the time taken for the search. If the goal is not reached, the algorithm proceeds to explore the neighbors of the current node. It does so by creating new paths, appending neighbors to the current path, and pushing them onto the stack for further analysis. Similar to the BFS algorithm, DFS ensures each node is only visited once by making it as a visited once explored. The time complexity of DFS depends on the structure of the graph and the ordering of the nodes, but in the worst case scenario, it can be big O of V plus E, where V represents the number of vertices, that is nodes, and E represents the number of edges in the graph. While the space complexity can be big O of V, where V represents the number of vertices in the graph. Based on the above test cases, we can analyze and comment on the performance of each algorithm in terms of path efficiency, computational time, and suitability for different types of searches. First, coming to the breadth first search, BFS is guaranteed to find the shortest path in terms of the number of edges traversed, which is evident in the scenarios where direct connections exist between the nodes. However, it does not consider the weight of the edges, which can lead to suboptimal paths in weighted graphs. The time complexity of BFS is generally good for unweighted graphs, but it can be inefficient in large graphs because it explores all neighboring nodes level by level. BFS is best suited for unweighted graphs where the goal is to find the shortest path in terms of the number of edges. Next, coming to the depth first search, DFS does not guarantee the shortest path and can result in paths that are longer than necessary, as seen in the test cases, where it takes a roundabout way to reach the goal. DFS can be quicker in finding a path due to its aggressive exploration strategy, but the path found may not be optimal. Its performance in terms of time seems competitive in the provided test cases. DFS is suitable for exploring all possible paths when the path's length is not a concern. It is not recommended for finding the shortest path in weighted graphs. Coming to the Dijkstra's algorithm finds the shortest path in terms of cumulative weight, which is determined by its ability to consistently find efficient routes in the test cases. It generally performs well, but can be slower than the BFS or DFS due to its need to constantly select the minimum weight node from the priority queue. The performance is still quite efficient in the test cases. Ideal weights for weighted graphs without negative weights where the shortest path is needed. A-star algorithm uses heuristics to guide its search, making it efficient at finding the shortest path in terms of cumulative weight. This is shown by its performance, which matches or surpasses Dijkstra's in the test cases. While A-star is designed to be faster than the Dijkstra's, by focusing the search, its time performance heavily depends on the heuristic. In the provided test cases, it's competitive, showing only slight increase in computational time compared to Dijkstra's, likely due to the heuristic calculation overhead. A-star algorithm is best suited for the weighted graphs where an appropriate heuristic is available. It's especially effective in large search spaces due to its prioritized exploration.
I'm now going to talk about future scope for our project. In terms of integration with the real world, our project currently operates within a simulated environment, and we hope to use real world geographical data and maps to enhance applicability. This would mean that if we could use graphs that represented the map of a city, we could essentially find shortest distances between 2 points in a map. We also hope to improve our algorithm. Building on the foundational algorithms explored, we could find out about more algorithms which are more complex and could perform better. We hope to incorporate some machine learning algorithm which could help in predictions, and that would help us use other variables such as traffic, weather, and these things could aid in finding the shortest path. We would also like to use a better user experience and provide an interface for the user to interact with the tool that we could build. Scalability and performance optimizations would help us take this to the next level and make it more efficient when processing large scale graphs, which could represent bigger, busier cities. And application of diverse domains refers to extending the application to various domains such as emergency response, logistics, city planning, wherever we could provide valuable contributions.
And with that, we've reached the conclusion of a project on evaluating pathfinding algorithms for efficient route planning. In this project, we set out to evaluate the effectiveness of various pathfinding algorithms including breadth-first search, depth-first search, Dijkstra's and A-star for efficient route planning. Through diligent implementation and comparison, we aim to uncover an optimal strategy that minimizes both cost and time in navigation scenarios. This endeavor has not only deepened our understanding of algorithmic design, but also illuminated the nuanced demands of efficient route planning in today's complex networks. The preliminary results underscore the immense potential of algorithmic solutions in transforming transportation and data flow, marking a significant stride towards optimizing navigation systems. As we move forward, we are excited to continue exploring this frontier, pushing the boundaries of what's possible, and ultimately revolutionizing the way we navigate our world. Thank you.